7C.6. I have to break up the notes because the notes are so long that if I try to do it in one sitting on a Monday, we just wouldn't get to it all. Now, I could just jump to the problems and show you that, but there's part of me that needs to show you. I'm inclined to show you where some formulas come from. Because of that, that is why I wanted to show you a proof. Give me a little bit of time. It's going to take me about 5 to 10 minutes for that. But let's talk about what we're going to be doing. We're going to be simplifying problems. And in the problems that you simplify, some of you like puzzles. Some of you like looking at things and trying to figure out, how do I simplify this? You're going to be looking at these like brain teasers. And some of you like brain teasers, and you're going to be great at this. And some of you get frustrated by brain teasers because they don't come easy. This section, the next two sections, are not going to come easy if you don't like brain teasers. So keep that in mind as we do these problems. First thing I need to let you know in these set of notes, reciprocal identities. If you ever have a cosecant in the denominator, you can move it up using its reciprocal identity. Cosecant is the cousin to sine, and if it's in the denominator, you can always move it up by switching it over to its cousin. Or vice versa. If cosine's in the denominator, you can move it up if you're using secant. If you have cotangent in the denominator, you can move it up to be tangent of the same angle. That's going to be helpful if we ever have something in a denominator and we want to get rid of the fraction. Quotient identities are another way to look at tangent and cotangent. Sometimes it'll be helpful for us to switch tangent into sine divided by cosine. Sometimes things are a lot easier in terms of sine and cosine, especially when it comes to simplifying and dividing. So we are going to use those 8 things quite often. The only thing that's new that we have not covered before are these 3 identities that are called Pythagorean identities. These are the most popular trigonometric identities that are in trigonometry. Okay? When I think of SOHCAHTOA being for the triangle, that's what these are when it comes to the unit circle. Sine squared of theta plus cosine squared of theta is always equal to 1. Tangent squared of theta plus 1 is always equal to secant squared of theta. 1 plus cotangent squared of theta is equal to cosecant squared of theta. So these 3 formulas I am going to recommend that you memorize. Because they are going to be inside of other problems. As you do the problems that are on worksheet 7 and on worksheet 6 and on the review, if you don't know these things, it makes it that much harder to do the problems. It makes it that much harder to do the brain teasers. Okay? Now, I wrote a little side note on the Pythagorean identities because most Pythagorean identities are not this straightforward. They are usually in the form of 2 terms. Let me tell you what I'm talking about. Meaning, you're not going to see it like this. You are going to see it like this. 1 minus cosine squared of x is equal to blank. There are only 2 terms here. There's a missing term. It's equal to something. They are using this first Pythagorean identity, and there's only 2 of the terms. Whoever wrote this question, me in this case, I subtracted the cosine squared from this side to this side, and so what is that equal to? I'm hoping you see it is the same thing as the sine squared of x. You can take it from 2 terms down to 1 term if I know that Pythagorean identity. So now let's check to see if you understand what I just did. What if I had secant squared of theta minus tangent squared of theta equals blank? Don't say anything. Just look at it. the secant squared of theta minus the tangent squared of theta. You're going to maybe use the second one, and you're going to figure out what is that equal to. Don't tell me. Tell the person you're sitting next to what you think it is. If you and your partner said 1, please raise your hand. Ooh, that's over 80%. That's 80, 90% of the class. Wonderful. Good. Let's make it harder. Slightly harder. Not much harder at all. Okay? What about cotangent squared of theta minus cosecant squared of theta equals blank? Think about your answer. Don't say it. Come up with your own. Now tell the person you're sitting next to and why if you disagree. Go ahead. How many of you put -1 or said -1 with your partner? Raise your hand, please. That's over half of you. I still think that's in the 80% range, and I'm okay with that. You will need to get used to seeing these Pythagorean identities, and it's way better if you have them memorized because they're not going to be given to you at all on any quiz or test or worksheet. So with that being said, that brings us to, well, where do these things come from? I want to definitely show you where they come from because I hate teaching you something unless I show you where it comes from. So this is what I'm going to do. This is a do not write. This is something I only want you to see because you are bright enough to see where this formula is derived from. The word derived means where does this formula come from? And it can be used on anything. We're going to derive this Pythagorean identity. So here is what we're going to do. I'm going to draw a triangle inside a circle. And this triangle could be in quadrant 1 or quadrant 2 or quadrant 3 or quadrant 4. It doesn't matter. And I'm going to call the angle that the triangle makes, I'm going to call it theta. It could be any angle. And the distance that it goes in the horizontal direction, I'm going to call x. The distance it goes up, I'm going to call it y. And then the distance out here to the edge of the circle, I'm going to call it r for radius, by the way. And so I want to start first and foremost by using the Pythagorean theorem on these 3 variables. These 3 things are related to each other by the Pythagorean theorem. I'm going to use a squared, which just so happens in this case to be x squared, plus y squared is equal to r squared. That works for this triangle. That could be anywhere. Then I know that the sine of this angle is equal to the opposite. Waiting for my marker to show up. The opposite, hypotenuse, adjacent. If I use SOHCAHTOA, the sine of theta is the opposite of hypotenuse, or y over r. If I were to solve that for y, I would multiply by r, and I know that y is equal to r sine of theta. The cosine of theta, on the other hand, is the adjacent over hypotenuse, or x over r. And if I were to solve that for x, I would multiply by r and get r cosine theta. Now, if I were to substitute, since I know what y is and what x is, I can actually plug this in for the y up there and plug this in for the x in that equation we started with. So instead of x squared, I'm going to use r cosine theta squared. And I'm going to add, instead of y squared, I'm going to put r sine theta squared, and that is equal to r squared. I'm going to simplify it. R squared cosine squared theta plus r squared sine squared theta equals r squared. The last thing I get to do is divide by r squared. What happens when r squared goes into r squared? It becomes 1. It becomes 1. And guess what I get? I get cosine squared of theta plus the sine squared of theta is equal to 1. And this is your first Pythagorean identity. Make sense? That's where it comes from. What I'm going to do next is I'm going to take that first Pythagorean identity and I'm going to divide it by cosine squared of theta. So I had cosine squared of theta plus the sine squared of theta. You could write that in either order, doesn't matter. And I'm going to divide each of these by cosine squared of theta. Divide by cosine squared of theta. Divide by cosine squared of theta. What is cosine squared of theta divided by cosine squared of theta? What is sine squared of theta divided by cosine squared of theta, maybe using one of your quotient identities? Tangent squared of theta, because sine squared divided by cosine squared should equal tangent squared. Equals, what's 1 divided by cosine squared? If it's in the denominator, I want to move it up. What's it going to be? And then don't forget, if it was squared, you still have to have it squared here. Guess what that is? That is our second Pythagorean identity. We have our first Pythagorean identity. We have our second Pythagorean identity. To get to our third one, take the first Pythagorean identity. Remember, I had cosine squared of theta plus sine squared of theta is equal to 1. And instead of dividing by cosine squared, I'm going to divide by sine squared. Divide everything by sine squared. And let's simplify using our quotient identities. Cosine squared divided by sine squared is? Don't forget, squared, squared, that cotangent has to be squared as well. So be specific. Plus, what does that go in?
1.
And I want to move it from the denominator to the numerator, but it's squared. And guess what that is? That is our third Pythagorean identity. One way that I actually memorize the third one is I think of the cotangent and the cosecant are co-captains. The cotangents are together, whereas secant and tangent are together as well. Sine and cosine, they're meant to be together too. There you go. So this is where I'm going to end your notes for today. That's as far as we're going to get.